Hello. So in this video, I'd like to talk about some constructions we can make now that we have introduced this natural numbers number system. So let's get right to it. Okay. So the first definition is that of a sequence. So sequence is a function whose domain is natural numbers. So that might be a slightly different way than how you imagined sequence. But so if you have a function from natural number to any set A, we usually don't use the functional notation. So we don't use f of 1 or f of 2 so much in that situation. It's more common to use these notation, braces a sub n, where n is changing from 1 to infinity. So you kind of think of as a list of numbers or list of outputs that is indexed by natural numbers. So that's a more common way to write down a sequence. The textbook points out correctly, I think, that this is inconsistent with our set notation. So the problem here when we use notations like this is that we make it look like this is a set. So remember, in a set, the order in which the number appears does not matter. And also repeats do not matter. So you could have a finite set, right? If an is, for example, -1 to the nth power, this will flip back and forth between -1 and 1. There's only 2 elements in the image of the set. But we want to think of a sequence as something where order does matter, and some numbers could appear twice, and that's different from just counting it once. So although this is way more popular notation, book uses either angle brackets or just kind of lists it off as separated by comma to indicate that this is a sequence. So some book uses these notations, but I gotta admit, this is the notation that uses braces is far more popular, and you have to tell yourself that that's different from a set, it's a sequence. Okay. So we've already introduced summation notation. So that's using the Greek letter capital sigma to indicate like a repeated addition. There's a similar notation for products where you multiply lots of different elements in a sequence. And that's using the Greek capital letter pi. So pi equal to 3.14. This is usually the lowercase p for the Greek letter. The capital pi looks pretty, slightly bigger, and it has straighter legs than the lowercase counterpart. And when you use that notation instead of sigma, it's p for product. So you multiply them. One notation that's probably even more popular than this is what's called the Factorial Notation. So if you just multiply 1 through any natural number n, the product is usually denoted with this exclamation symbol, and it means multiply 1 through n. That's factorial. One piece that I want to kind of highlight that sometimes comes up is the first one is very reasonable. If you don't add anything, then the empty sum is considered 0, so because 0 is the additive identity. If you start with a 0, and if you don't add anything, then it is itself 0. If you have an empty product, if you think about it long enough, I think you'll come to the same conclusion as well. But if you don't multiply anything, you should get 1, because 1 is the multiplicative identity, right? If you had started with 0, then 0, if you multiply in any number to 0, you stay at 0, so you always get 0. But if you start with 1, when you multiply in other numbers, a1, a2, and so on, you'll get the product you expect. So empty product starts at 1, so that's a thing that you should know. Okay, and you could do summation with things other than natural numbers or a finite set of natural numbers. You might add over different types of sets. So it could be multiplying all the prime numbers, for example, or you want to multiply all the numbers divisible by 5. So if you have a different set that you want to add over, not consecutive integers, then you could rewrite the summation notation. So you rewrite it in such a way that you have your index variable that belongs to some index set. So you want to describe the set first that you're adding over, and then you can rewrite it like this to indicate that you want to sum all over every element of I, capital I. And sometimes authors get lazy and they don't write I belongs to capital I, or maybe they just write the name of the set that it's summing over. That's a very common notation as well. So I in this case is called the index set, but it could be, you can name the index set whatever you want. When context is clear of what you're summing over, some authors get a little bit lazy, and sometimes people write summation notation with, you just write down what the index variable is of summation. So sum over all of the i's, ai. Or they may get even lazier and don't even write down the variable. Because if you write it like this, maybe it's clear that index is the I. This is, so I understand why the authors do it. So maybe sometimes it's a little bit lazy, but it also clutters up the notation as well. If you're talking about things like statistics and you're summing over data set, maybe it's clear that, hey, of course I'm adding over all of the available data set. That's what I mean by summation. But if you're talking about other more advanced mathematics, sometimes it could get confusing. So I don't like these type of ambiguities, but I have to teach you this because it's a very common omission. And like one big drawback of writing out, so all of the subscript and the superscript of the summation notation is that it makes it very difficult to do inline typing when you're doing mathematics. You almost always have to do the display style to get everything in and make it clear to read. So I think that's part of the motivation why you omit some of these notation to make it a little bit cleaner. Okay, we're not talking about infinite sums or products in this chapter because to do that, we have to use the idea of limits, and we haven't got there yet. I do intend to talk about limits, but maybe at the very end of this course. So 10th week when we're talking about real numbers, when we start to discuss this ideas of limits. So infinite sums and infinite product, you don't have to worry about how they're defined. But there are other things that we could do. Like we've talked about unions and intersections, and you could definitely do this for infinitely many infinite index sets. So for example, if we write the big union symbol with the index starting point and ending point, maybe even if you haven't seen this, maybe the meaning is fairly clear. That means that you take the union of A1 and A2, and once you're done, you take the union of that with the A3, and so on, until you take union of all the sets A1 through AN. So that's how you can compactly write lots of unions. And it doesn't even have to be finite. Even if index set is infinite, like for all of natural numbers or all integers or all real numbers, you could actually make sense of this. So then the definition has to change a little bit. Like you can't get to the definition with finitely many steps. Instead, you use quantifiers. So we say that X belongs to this union of AIs for I in some index set I, if there exists an index I in the index set such that X belongs to that set. So if you can find at least one set that contains X, then it's contained in the entire union. So union is kind of synonymous with existential quantifier in this sense. And if you rephrase it this way, then I doesn't have to be finite. It could be infinite, very big sets. And this is well defined. The reason why I say well defined is that set is well defined if you can decide if an element belongs to it or not. And then the test of belonging to it or not is kind of transferred over to this existential quantifier. So I hope that made sense. And you could do a similar thing with intersections as well. So if it's finite, maybe it's clear what you should do. But even if it's infinite, you could reinterpret this. If X belongs to intersection of all the AIs, that is equivalent to asking for X to belong to every single set in the index, every single AI. So you use not existential, but universal quantifier. For X to belong to this, it has to belong to every single possible AI that's in there. I hope that makes sense. And if it's not clear to you why union is existential and intersection is universal quantifier, you could kind of think of maybe just go back to a smaller example. What does it mean to belong to A1 union A2? Well, it belongs there if it's in A1 or A2 or both, right? So if you can find at least one index where X belongs to AI. If you want to check if an element belongs to intersection of A1 and A2, then it has to belong to both A1 and A2. So for all index I, X belongs to AI. Okay, so just kind of practice using this idea. So suppose we take a union over all positive R greater than 0. and we take a union of all the intervals from negative r to r. So this is a union, so that means you belong to this set as long as you're contained in one of the intervals negative r to r. Well, r could be very big, right? So for any number x, if you can find a bigger number that contains where x belongs to that interval, then it's in it. And all real numbers would be in it. So this infinite union is equivalent to the entire real number set. I hope that made sense. If you do a similar infinite intersection instead of union, for you to be in the set, you have to be included from between negative r and r for any positive number r. And there's really only one number that does that, and that's 0. If you pick any other number, let's say this is the real number line. If you pick anything other than 0, then you can draw an interval from negative r to r small enough that it excludes that number. But 0 is always contained in all of these. So the set is a singleton set, 0. Okay. One thing I want to mention about summation and products and these unions and intersection is that the letter we use for indexing doesn't really matter. You could use a different letters for the index as well. So if you write the summation with the letter I or letter J, as long as you're not changing the index, the numbers you're adding with, then it doesn't matter. They mean exactly the same thing. If you've taken Calculus 2, this is the same idea of definite integrals. You could use any letter for the variable, or sometimes called dummy variable. And it means exactly the same thing. You're looking at area underneath the curve. So it's similar thing here. Sometimes it's convenient, or maybe it's insightful to relabel it and work in a different way. Here's one example. In the last set of videos, we proved a formula of what you would get if you add up all the numbers from 1 through n. And you could do that using some summation trick with relabeling. So here's the insight. If I changes from 1 through n, as in the summation notation, that's the same thing as j, where j is n plus 1 minus I. So if I is equal to 1, j is equal to n. And as I counts up, j counts down, all the way down to 1. When I is equal to n, j is equal to 1. So j is counting the same set of numbers, except you're just counting backwards. Okay, so let's use this idea. So if you have twice the sum from 1 through n, that's the same thing as adding 1 through n to the sum of n through 1, counting backwards. The order in which you add here doesn't matter. And you can rewrite the j. J is the same thing as n plus 1 minus I. So you could replace j with that expression if I wanted. But if you're adding I from 1 through n, and if you're adding n plus 1 minus I from 1 through n, you could do these summations together, right? You could do I plus n plus 1 minus I. And in fact, if you add these two things together, I and negative I cancels out, and we're just adding n plus 1 where I is changing from 1 through n. The summation no longer depends on I whatsoever. You're just adding n plus 1 n times. So the sum should be n times n plus 1. And now you might have noticed that this computation is equivalent to getting the summation formula that we proved earlier. The summation from 1 through n is exactly this expression divided by 2. So if you divide 2 over here, we got the formula we did last time. In the last video, we just kind of pulled this formula out of nowhere. But if you have some insight, maybe you can come up with a formula like this. By the way, this insight of adding the numbers twice, once forwards and once backwards, and then if you add it together, you get this constant n plus 1 over and over. This idea is done by Gauss when he was in elementary school, which I think is a cool idea. Anyways, I think I'm gonna stop the video here. I will see you a little bit later.